Today we're going to be talking about simulations, and simulations are actually ways that mathematicians and statisticians can take a something that can happen, some sort of a model, and we can recreate the chances of that happening. Now, this is how we design a simulation. We determine all the possible outcomes, we state any sort of assumptions, we describe an appropriate probability model for the situation, meaning we have to design one, and we define a trial for the situation and state the number that will be conducted. Now, some common ones that we think about are spinners. Okay, these are the ones you'll probably look at, spinners. We have, let's see, what else do we have? Coins. We can flip a coin if there's two different things. And we could also do, what other ones? Well, those are the two kind of common ones. There's a couple other different ways we can do it, but example one, it says, Allen made 70% of his free throws last season. Design a simulation that can be used to estimate the probability that he will make his next free throw this season. So a good way to do it would be a spinner, right? And the reason I pick a spinner is because we can actually just draw a circle, right? And we want 70% of that circle. Okay, so if you think of this is 75, right? We can just make it just a little bit less. And so we would say it's just about right there. So that counts for about 70% right there, okay? And so this portion, the 70% portion, is going to be a make, and this is going to be a miss. And then what we would do is we would add some sort of a spinner to it. Let's say here it is right here. And then we'd spin it around to see, is it going to land in the make or the miss? And you can actually do this multiple times to figure out, is he going to make the next one or not, right? And so we see these in kids' board games and all kinds of stuff all the time. All right, next one. It says, guided practice problem. It says a restaurant attaches a game piece to a large drink, awarding a prize to anyone who collects all 6 game pieces. Design a simulation using a geometric model that can be used to estimate how many large drinks a person would need to buy to collect all 6. So you're looking at more than one. Again, you could do some sort of a spinner. It says that pretty much they're all equal, right? So you just break it up into, that's a bad way to do it. You want it to be 6 pieces. So we would say this would be, there we go. So now we have 6 even pieces, right? 1, 2, 3, 4, 5, 6. And then again, like I said, we could attach some sort of a spinner to it and just say spin, and you would figure out which one they're going to get, okay? All right. Next one. It says a survey of East High School students found that 40% had brown eyes, 30% had hazel eyes, 20% had blue eyes, and 10% had green eyes. Design a simulation that can be used to estimate the probability of randomly choosing an East student who only has one of those eye colors. Well, again, like I said, a spinner is a really good way to do that. You're probably thinking this is the only way to do it. But using this distance learning, I can't really show you all the cool probability tools that our calculator can do. If you were bored someday or something, you could actually Google search some probability simulators. And there's all kinds of cool ones. There's coin flip ones, there's draw card ones, all kinds of different things like that, random number ones. But for our sake and for easiness, right, we're just going to pick these spinners. So if I look at a circle, remember in 3, we talked about a circle has 360 degrees, right? So I'm going to multiply that by 40%, so 0.4. And when I do that, I'm going to find the angle. Excuse me, that's 0.4. 144 degrees. So that means my first area is going to be about that big, and this is going to be for brown eyes, okay? That's going to be for brown eyes. Then the next one, 30% for hazel, so 0.3. right? We can go to our calculator, and that's going to be 108 degrees. So again, it's going to be about right there. That's going to be Hazel, right? Then the next one we're going to look at is blue, which is 20%. So that's going to be 72 degrees. Okay, that's blue. And then obviously the last one is going to be green. And I'll just write G for green. All right, and then we would attach some sort of a spinning object. And so what are the chances of picking the next one? And you'd spin it around, you could do this, okay? These are all perfectly good ideas for creating some sort of a simulation. Okay, here's a guided practice problem you could try as well. Now, what we're going to do is we're going to actually collect and summarize some sort of data from a simulation. Now, it says, conduct the simulation and report the results using appropriate numerical and graphical summaries. Make a frequency table and record the results after spinning the spinner 40 times. So let's say we took that spinner we did in example 1 and we spun it around and we found that he made 26 and he missed 14. So what we're going to do is we're actually going to look at the percentages of his makes, which were 26 out of 40. Now remember, he was supposed to hit 70%, but 26 out of 40 is definitely not 70%. This is equal to 65%. Okay? So, record the results so we can say that our simulation shows free throw percentage will decrease. And that is how statisticians and things like that will find that for other, we think about it in sports quite a bit. Also, thinking about the whole coronavirus thing and thing that we're all going through right now, it would be that, they're assuming that this spread is going to happen so quickly. We're going to have this peak. And what they're doing is they're doing simulations too. They're doing computer models, and they're basically having it show what it would happen, if one person spreads it to 3 people and so on and so forth. We have this huge spread. And so they're using simulations all the time. So this is super applicable to what we're talking about today. Okay. There's another guided practice problem you can look at. All right, now what we're going to talk about is something called expected value. Now, an expected value that you may know quite a bit is this one, GPA, right? GPA is an expected value. It's where you take what you got for a grade and multiply it by some sort of a weight, and you add them all together. Another way that's super interesting of expected value is your actual winning percentage on raffles and the lottery and stuff like that. So what that means is they figure out how many tickets they are, the cost of everything, and what your win out is. And normally the expected value for like a pull tab is for every dollar you are expected to lose 80 cents or something like that. I don't exactly know off the top of my head what it is anymore, but you're expected to lose or expected to win only 20 cents for every pull tab. Sometimes it's even less, but there's lots of different examples that we can do. Okay, so this is how we do it. We multiply the value of x by its probability of occurring, meaning if you look up here, okay, we're going to take our frequency, okay, frequency times its probability, and we do that for all of them, and then we add up the results, and so that's what we get. All right, so we're going to look at an example 4, and this one's a little bit time intensive, so just bear with me. It says, suppose that a dart is thrown at a dartboard. The radius of the center circle is 1 centimeter, so that little 5 guy in there is 1 centimeter, and every successive circle has a radius of 4 centimeters greater than the previous. Okay, so we're going to just look at each circle, and we're going to figure out their areas first, and then we'll multiply it by their point totals. So the first one, the little guy, has a radius of 1. So remember we talked about in the last one, area is equal to pi times the radius squared, right? So for our little 5-point guy, it's going to be pi times 1 centimeter squared, or just pi, right? Now, the next one, our 4-point. Okay, next one, 4 centimeters more. So pi times 1 plus 4 would be 5 squared. So that would be 25 pi, except for it doesn't include the one little pi before it. So we're going to subtract 1 pi from it. So it's going to be 24 pi. Okay, boom, pi, 24 pi. Next one, the 3-point total. Pi times another 4 inches from 5 would be 9 squared. So that would be 81 pi, except for I don't have the 25 pi from before. So that would be, well, 81 minus 25 off the top of my head. It's 56 pi. So this is going to be 56 pi is the area of the 3-point guy. All right, let's go to the next one. The 2-point is going to be pi times, well, 4 more than 9 is 13 squared. That's going to be 169 pi, except for I don't have the 81 pi from above. And so 169 minus 81 88 pi. So this guy right here is 88 pi. And then finally, the last guy, well, 1-point guy, is another 4, so that'd be 17 squared. And so we'd say 17 is 289 minus the 169 pi from before. And so you'd get 120 pi. Okay? Now what we have to do is actually figure out what each one is expected to get. So what that means is I'm going to take my first number, that's point total, times the area. I'm going to multiply that by 5. I'm going to do this over here, and I get 5 pi on the first one, plus the next one is 4 times 24 pi, which would be 4 times 24 would be 96 pi. The next one, 3 times 56 is going to be 168 pi. 2 times 88 is going to be 176 pi. And then the last one is going to be 120 pi. So I add up all of those, and I'm actually going to get rid of the pi too in my answer. So let's put all those in. So we're going to say, so 5 pi plus 96 pi plus 168 pi plus 176 pi plus 120 pi equals 1,774. Well, rounds up to 1,775. So our expected point value is 1,775. Okay. So that's the from each. Well, that's the total right there. Okay. All right. Now it says For part B, it says design a simulation to estimate the average. Okay. And so what we can do is we can actually just figure out the outcome of region 1, which remember that was pi. So 16 times pi would be 16 pi. Then the next one was 5 pi. So times 13 would be 65 pi. And then the next one was, let's see, going up here, 56. Oh, that was 24. 24 pi times 13. I was wrong with that. So 24 times 3. 72. So that was actually 72 pi. Okay. Then the next one, 13 times, what was it? 56 pi. That was 728. Okay. Then the next one was 8 times, 88. So that was 704 pi. And the last one was nothing, so it'd just be 0 pi. And so when I add up all of those, I end up getting, let's see, it was 16 pi plus 72 pi plus 728 pi plus 704 pi. So 4,775, which is much bigger. Okay, so how does this compare to the expected value found in part A? Much larger. Okay, if you have any questions, let me know. Otherwise, good luck on your assignment.